Welcome to the presentation on the group investigation model in chemistry learning. This presentation explains how rigorous inquiry can be combined with a democratic classroom process, and how the model can be applied in senior high school chemistry. The focus is on helping students investigate, collaborate, reason from evidence, and reflect on their learning. This slide explains the educational context. Chemistry learning is challenging because students need conceptual understanding, laboratory skills, collaboration, evidence-based reasoning, and reflection. Group investigation is appropriate because it turns the classroom into an active inquiry community where students investigate real chemical problems and construct knowledge together. The learning objectives are organized into 4 main targets. First, students define the meaning and principles of group investigation. Second, they identify its theoretical foundations. Third, they describe the 6 instructional phases. Fourth, they explain teacher and student roles, analyze learning effects, and apply the model to senior high school chemistry. At a glance, group investigation is a cooperative, inquiry-oriented, and democratic learning model. Students work around meaningful and puzzling problems. They do not simply receive information, they negotiate ideas, examine evidence, and reflect together. This model integrates academic learning with social learning. The intellectual roots of group investigation come mainly from John Dewey and Herbert Phelan. Dewey emphasized learning through active experience, inquiry, and democratic participation. Phelan viewed the classroom as a miniature social system where students practice democratic citizenship through roles, evidence, and shared conclusions. This slide presents the core assumptions of the model. Learning is social and collaborative. Meaning is constructed through interaction and inquiry. Academic and social development happen at the same time. Students also negotiate roles, evidence, and conclusions, so classroom learning becomes both intellectual and democratic. Inquiry begins with a puzzling situation that encourages students to ask questions. In chemistry, this may involve an unexpected reaction, a surprising observation, or a problem that requires evidence. Knowledge is actively reconstructed through data, discussion, experimentation, and reflection, not passively received from the teacher. The group investigation model consists of 6 phases. Students first encounter a puzzling situation, then explore reactions, and formulate study tasks. Next, they organize groups, and conduct independent and group study. Finally, they analyze progress, reflect on findings, and recycle the inquiry cycle when new questions appear. Phases 1 and 2 focus on puzzlement and initial reactions. Students observe a meaningful chemistry phenomenon and express their first ideas. They identify different viewpoints, share prior knowledge, and formulate investigative questions. The teacher encourages curiosity without directly imposing the final problem definition. Phases 3 and 4 focus on organizing and investigating. Students define the problem, negotiate subtopics, assign roles, plan procedures, and conduct experiments. In chemistry learning, group roles may include coordinator, researcher, lab safety officer, data recorder, and presenter. The goal is safe, evidence-based inquiry. Phases 5 and 6 emphasize reflection and recycling. Students analyze the quality of their evidence, evaluate group collaboration, revise hypotheses, improve procedures, and ask new questions. This rolling model shows that group investigation is not strictly linear, it can move back and forth as understanding develops. Group investigation turns the classroom into a miniature democracy. Students exchange ideas authentically, make decisions together, and use reason and evidence to reach shared conclusions. Every student is treated with equal dignity, while the teacher maintains educational boundaries and supports productive inquiry. The teacher has three important roles: counselor, consultant, and friendly critic. As counselor, the teacher helps clarify problems. As consultant, the teacher supports group organization and participation. As friendly critic, the teacher encourages reflection and deeper meaning. The key is to guide students without taking away ownership of the inquiry. During group investigation, teacher responses must be flexible and context-sensitive. The teacher asks probing questions, helps clarify hypotheses, guides data collection and analysis, and monitors scientific accuracy and laboratory safety. The teacher supports inquiry while allowing students to think and decide independently. Successful group investigation requires several resources. Information resources include textbooks, journals, databases, and multimedia materials. Human resources include teachers, laboratory assistants, experts, and peers. Investigation resources include safe chemicals, tools, and protective equipment. Digital resources support data analysis, collaboration, and presentation. The expected learning effects are both instructional and nurturant. Students develop constructivist understanding by gathering evidence and testing hypotheses. They also develop group governance, independence, respect, trust, and a habit of collaborative inquiry. Thus, the model supports both chemistry achievement and democratic character development. This slide summarizes the strengths, challenges, and solutions. The strengths include active learning, higher order thinking, real-world chemistry connections, collaboration, and independence. The challenges include time, resources, facilitation skills, and unequal participation. Solutions include starting small, teaching roles, using rubrics, building autonomy gradually, and monitoring safety. In chemistry, group investigation can be applied to reaction rate. Students investigate why the same reaction may occur at different speeds under different conditions. They may examine temperature, concentration, surface area, and catalysts. The expected products include hypotheses, safe procedures, data tables, graphs, conclusions, presentations, and individual reflections. This slide connects investigation to assessment. In the first phases, students observe phenomena and formulate questions. In the middle phases, they form groups, plan, and conduct experiments. Then they evaluate evidence and collaboration. Finally, they revise, extend, and present their investigation. Assessment covers hypotheses, design, safety, data analysis, collaboration, presentation, and reflection. To conclude, students do not only learn chemistry through group investigation. They also learn how to investigate, collaborate, decide, and reflect. The model is especially useful when chemistry learning requires both scientific reasoning and democratic participation. Thank you for following this presentation. The reference slide lists the main sources used to support the presentation. These sources include works on chemical laboratory safety, group investigation, cooperative learning, inquiry-based learning, reaction rate learning, and models of teaching by Joyce, Weil, and Calhoun. These references strengthen the theoretical and practical basis of the presentation.